My name is Eamon McShane, and today I'm going to be presenting on the sequential criterion for continuity, and how this relates to the importance of the counterexample in mathematics and the place of proofs in mathematics. So to start off, what is the sequential criterion for continuity? It's a theorem that states that the following three statements are logically equivalent to one another. That is to say, the truth values of these three statements are the same. If one statement is true, all three are true. If one statement is false, all three are false. It states that a function f of x is continuous at a point x naught. A function f of x has a limit at x naught equal to f of x naught. And for any sequence x sub n in the domain of a function f of x, the sequence converging to x naught, the sequence f of x sub n converges to f of x naught. To put it in slightly more layman's terms, a function being continuous at a point is equivalent to saying that the limit of the function at that point is the value of the function at that point, which is equivalent to saying any sequence contained in the domain of f converging to the value of the point, the function of that sequence converges to the function of the point. Why is it important then to be rigorous about this? I think to talk about this, it's important to talk about why the sequential criterion for continuity matters. The high concept answer, perhaps, is to say that it creates some kind of a bridge between limits, continuity, and sequences. These are two very different fields at first glance. Limits and continuity are certainly more of your standard early calculus 1 fare as you work your way up to derivatives. Sequences, on the other hand, are not seen that much. You do get a little bit of series when you're talking about Taylor series approximations, but sequences don't really come up in calculus at all. In that sense, the sequential criterion for continuity provides a way to lump sequences in with calculus. But again, that's somewhat high concept. There is a much more down-to-earth and grounded reason why the sequential criterion is very important, and it has to do with proofs. If you were to be a Calculus 1 student, you would probably be familiar with the epsilon delta definition of the limit. You probably hear it brought up, and maybe you do a problem about it, and you put it out of your mind because it's kind of complicated and it requires you to go through all sorts of steps. It's not a very elegant proof, but it is very effective. You have a similar epsilon delta definition for continuity. What the sequential criterion for continuity allows you to do is bypass this. And specifically, it allows you to do so in a very nice way when a function is not continuous at a point. This is because of a very important fact about proofs. It's very easy to disprove a wide sweeping statement. You will notice in the sequential criterion for continuity, the third statement says for any sequence in x sub n that converges to x naught, the sequence f of x sub n converges to f of x naught. That is a big claim. That is a very big claim. And it means you only need one counterexample to shoot the whole thing down. The point, in that sense, of the sequential criterion is that it turns a problem that is very complicated into one that is very simple. And when you're simplifying a problem in this way, you need to make sure that it is a simplification that you can make. In an example that would be very applicable to earlier mathematics, if you have the function x squared minus 4 over x minus 2, you can factor your numerator, cancel out, and you're left with x plus 2. You've simplified your function into one that is linear and very easy to understand. But you cannot forget that you have divided by x minus 2. If you were to plug 2 into that function, that initial function, you would get something that is undefined. So your new function has to remember that and keep that undefined point at 2, else you oversimplify the function. In order to avoid oversimplifying what continuity and limits are and how to disprove them, you need to be certain that you're being rigorous when dealing with the sequential criterion. The other main point as to why you need to be quite rigorous in the sequential improving the sequential criterion is that it is a type of proof that is valuable to understand what it means. You're saying that these two statements are logically equivalent. You are proving essentially an if and only if. You are saying if one is true, two is true. If two is true, one is true. That is a very powerful relationship, and it's one that it serves you well to understand how to go about proving. It's also part of the reason why this proof can be very hard to intuit. As I mentioned before, and the very high concept reason why this is important, limits and continuity kind of naturally come in a package. You learned them very early in calculus. They form essentially the basis of early calculus, eventually leading up to derivatives. Sequences, on the other hand, feel very disjoint. It's kind of difficult to figure out how to intuit linking one and the other. You can very easily create a proof that links the continuity part and the limit part of the sequential criterion, and leave out the sequence part, which gives it its name. The way that you wind up having to approach this is almost a cyclic proof, showing that statement 1 implies statement 2, which implies statement 3, which implies statement 1 again, where you create now this cycle of you can start from any one of those statements and loop around to the other two. It's not a technique that most people are likely to think of when they first see it. They're likely to try to brute force it and to get some way to link them all up with each other, and they're going to be frustrated by the attempt to do more work than is necessary. When proving this, I also had an AI go through the proof, and I think there are a couple of interesting things to note about what the AI did correctly and what it did incorrectly in relation to that notion of intuition. The first thing I should start with is that the AI was correct. That's a very important thing to start with, I think. I think it would be disingenuous to lead with anything else. The AI proof, it's logically sound. There's no logical basis on which to challenge it. I'm not going to be attacking it on the basis of did it do the job correctly. I'm going to be attacking it on the basis of did it do the job in a way that is understandable, that conveys meaning to somebody who doesn't really know what these terms are. It also has a unique and interesting way of proving the theorem. It goes about it in a way that you wouldn't see in a textbook, or that isn't the most natural way for a student of real analysis to go about proving this. I think that is a strength, that it explores a different path and shows you what other kinds of proof techniques you can actually use to understand what's going on here and form these relationships. And lastly, the proof is concise. It doesn't meander. It uses definitions to cut down on time. It's overall a very strong proof to a real analysis student. And I think this is where that conditional is the failing of the AI. It doesn't go about things in an intuitive way. It doesn't attack the problem in a manner that somebody without an existing basis could understand. It makes jumps in its logic. It skips steps that probably shouldn't be skipped. It doesn't state certain definitions that might need to be stated. Uh, Again, this doesn't necessarily make the proof invalid, but it does make it harder to follow. The other thing that I noticed about the AI proof is that it does use a proof by contradiction. It does something that somebody who isn't super familiar with proving probably wouldn't think to do or even know how to do immediately. Uh, this does, again, just make it that much harder for somebody new to come in and understand what the AI is saying. So the question ultimately is, why does this matter? It's easy to talk about why it matters in a mathematical context, but it's also important to understand why it matters outside of math. And I think there are two. This is a twofold question. I think the notion of the counterexample is something that is incredibly valuable, even outside of math. Being able to look at big sweeping statements and be able to just poke holes in them and understand that one counterexample can topple an entire structure, that's valuable, especially in a day and age where we are bombarded by big sweeping statements that big sweeping stereotypes, big sweeping statements about economies and politics that are designed to give the impression that it is all or nothing. The counterexample says that it is never all or nothing. As long as you can find one thing that doesn't agree, you have any number that open up to you. The sweeping statement itself falls apart. Being able to just know that this is something you can do and knowing that you can look for this and knowing that you should be looking for this, that kind of critical thinking is important. And the sequential criterion, even if it really doesn't apply necessarily itself to any of these real world scenarios, it is a very important tool for being able understanding the sequential criterion is understanding how to reframe a problem as, oh, from I have to push forward and prove this entire statement, I have to push a boulder up a hill, to I just have to find one brick that will turn the hill into flat ground so I can push along nice and easy. I think the other reason why this matters is more to do with the AI part of this project. I do think initially there was the expectation that the AI would be convincing, but it would ultimately be misleading. It would say things that sound very true, but not necessarily have that logical basis for them. This is understandable. That is very common with AI, especially if you use it outside of mathematical fields. This is something that is frighteningly common. It can sink a lot of good work to take something an AI says at face value because it makes a very convincing sounding argument that falls apart the moment you start to prod at it. But I also think it's important to understand that that isn't the only pitfall that AI can fall into. That AI can sometimes give you correct information and obfuscate it by making it difficult to penetrate. It can skip steps, ultimately still giving you the correct answer, but not giving you any actionable information about how it got to that answer. and especially in an academic context, knowing how you got to the answer is oftentimes far more important than just knowing what the answer is. There is a reason math and physics and other STEM fields want you to show your work, because what ultimately matters is the understanding. It is one thing for the AI to give you patently wrong information, which you can easily fact check. It is another thing for the AI to give you correct information, but not tell you anything about how it achieved those results. It is ultimately a far more insidious thing for it to do, because it does give you your 90 on a test or 100 on your homework, but the next time you see it, you won't have learned anything. You won't have actually engaged, and that can be costly. I think for a proof that is ultimately designed around finding a new way to engage with an existing concept, the fact that the AI gives nothing worthy of engagement uh, is in some way ironic. Uh, Thank you very much for your time. Uh, my name is Eamon McShane, and this was my presentation on the sequential criterion for continuity.